Hello, we start this video with a slightly infamous question from my point of view, but I'll come back to that later on. Let's first of all get into the nitty-gritty of it. We've got a diagram. Let's see what's in the text that isn't in the picture. End of a horizontal hose pipe, height 1.3 meters. That's already there. Initial horizontal velocity of the water is 7. We've got that. Horizontal distance from the end of the hose pipe to the point where it hits the ground is 3.6. So they've put all of that on. Negligible air resistance. Draw an arrow to show the direction of the acceleration of the water at P. Okay, well, there you go. It's going to be straight down. That's easy enough. Mark this arrow A. Okie dokie. Describe the energy conversion that takes place as the water travels from the end of the hose pipe to the ground. So we've got gravitational potential energy into kinetic energy. That's what's going on there. Sometimes they like you to add in a little bit more and say things like, well, the GPE is a maximum at the top or something like that, or is a minimum at the bottom, these sort of things. I mean, that's kind of obvious when you've said it's included really in the GPE is going to kinetic energy. But there you go. Sometimes it doesn't do any harm to put in a little bit extra in case there's another mark floating around. C, explain why the horizontal component of velocity remains constant at 7 meters per second. So we can say there's no force acting in horizontal direction. So that's straightforward. You could say there's no acceleration in that direction, you know, whatever you might want, it's all the same thing. Show that the water takes around half a second to travel from the end of the pipe to the ground. I think there's a tendency for people to jump on this and think of the vertical motion, but you don't need to, because they've given us the horizontal component, which isn't going to change. So we're doing 3.6 divided by 7, so that's around about a half, isn't it, give or take? So that's what they were after. We can just look in the horizontal direction. Right, now we get to the last part, which is the aforementioned infamous part of the question. I do recall this question because it came up in a tutorial that I did, and the mark scheme on this particular question I just think has got a ridiculous comment on it, and I will get to that comment after I go through this. Right, so show the speed of the water when it hits the ground is 8.6 meters per second. Right, so my approach to this was to do conservation of energy. And as we've discussed previously, conservation of energy in projectiles, it turns into v squared equals u squared plus 2as, because we're saying, you know, if we start off with half mv squared, so our end kinetic energy is half mu squared plus mgh, then we cancel all the m's, we multiply everything by 2, and lo and behold, we've now got v squared equals u squared plus 2as. So you can use this equation as it is conservation of energy. So I looked at this and thought, well, if you're doing a conservation of energy, it doesn't really matter about, you can do this across directions. You don't have to stick, we're not sticking to, oh, let's look at horizontal or vertical. We're just dumping it into that equation because it's an abridged form of conservation of energy. So you just say, okay, conservation of energy, and then you can say that v squared equals 7 squared plus 2 times 9.81 times what is our h that we've got, so 1.3. Right, so we put all of this in. So what do we get? We've got 2 times 9.81 times 1.3 equals 25.5. Add on 49 equals that. Do the square root, and we've got 8.6. So that to me seems a perfectly reasonable approach. And yet on the mark scheme for this, because clearly you've got someone with, I don't know, very little imagination or maybe little thought of how physics actually works, they specifically say on the mark scheme, keep an eye out for this approach because it's wrong physics, which is quite a statement to make when it isn't wrong physics at all. I might have some sympathy for that if people haven't stated conservation of energy at the beginning. And I suppose to be safe, you could put in the full version here with all the M's and the halves and all of that sort of stuff. But that is, well, frankly, I think it's just a ridiculous thing to have on a mark scheme where you're going to have markers going through and say, I think this is 3 marks at the end of the question. And say, oh, well, you can't have that because we've decided that this is wrong physics, even though it isn't. So yeah, as I say, that was my approach for it. I mean, you don't have to do this. Obviously, you could work out the vertical component of the velocity, which is this conversion, which this bit here is what is being added on to the kinetic energy. That's your mgh, which is being put onto the kinetic energy. And then we end up doing the same Pythagoras type approach in order to get what v squared is. So both of those solutions are fine. But yeah, it just really annoys me when you get these things on exam mark schemes and they're just going to take marks off of people for perfectly good answers. I mean, I could go on for quite a long time about the number of ways they do that, but this is one of the worst. Okay, on to what's hopefully a less controversial question. Start with a couple of definitions. We've got define velocity, so rate of change of displacement. You should get familiar with all of those. Define work done by a force. So the work done is the force multiplied by the distance moved in the direction of the force. So they're 2 definitions that should be gimmies. Right, figure 3.1 shows a rider on a sledge sliding down an icy slope. Frictional forces acting on the sledge and the rider are negligible. We've got they've drawn on the forces on the force diagram. Explain why force N does no work on the sledge as it slides down the slope. Right, so we need to say that it is perpendicular to direction of motion. So that fits in with the definition of work that we gave earlier in the question. State and explain the force that causes the sledge and rider to accelerate down the slope. So it's the weight that's causing it because it has a component, because a component acting down the slope, acting down slope. So that's all fine. Then we've got a velocity time graph for this sledge and rider. Use this to determine the acceleration. So the acceleration is the gradient. What gradient have we got from here? We're going from 3 to 7. So we've got a change in 4 in the y direction, and that's over 2 seconds. So we've got 2 meters per second squared. That's our acceleration. What is the angle made by the slope to the horizontal? Right, so we've got a W. What we got? W. Does it? Okay, so W sine theta. That's our resultant force down the slope. That is going to be equal to the mass times the acceleration. We've got now, okay, W is mg, so let's put that in, cancel the m's. We know that A is 2, so sine theta is going to be 2 over g. So we just need to put this in. I'm going to stick with, so 2 divided by 9.81 is equal to that. And then we need to do an inverse sine of that, and it's giving us about 12 degrees. So it's 11.8 degrees, so 12 degrees looking, seeing as we've been pulling numbers off of a graph, let's not get too carried away with our accuracy. Right, the sledge crashes into a foam barrier at the bottom of the slope. Velocity of the sledge just before impact is 15 meters per second. They take that amount of time to stop. The average decelerating force on the sledge is that. Okay. So we have to calculate the mass. So we've got 510 newtons. That's our F equals ma. We need the mass, and then the acceleration is going to be 15 divided by 3.5. So that's what we've got with all of that. So 3.5 is 7 over 2. So if we say that's 30 over 7, so m is going to be 510 multiplied by 7 divided by 30. We can cancel those. Yeah, 3's do go into 51, that's 17. So we need to do 7 times 17, which is going to be 100, well, 70 plus 49, so 119. So let's just say that's, well, yeah, 119. What are they giving us on? They've only given us 2 sig figs here, so 120 kilograms for 2 significant figures. And we didn't even need the calculator on that one. Next up, we got a pulley. We got what we got here: 2 masses A and B tied together with a length of string passing over a pulley. A is held at rest on the floor, so everything's being held in place at the moment. They've given us the masses of A and B. Calculate the weight of mass B. Right, so a nice easy starter to get us going. So the mass of B is 1.5 kilograms. Multiply that by G, and we're going to get the weight. They've given us everything here at 3 sig figs. So let's put all that in 14.7. Yeah, 14.7 newtons. I'll leave it at 3 significant figures because that's what they've got in the question. Mass B initially at rest, 2.8 meters off the floor. Mass A is then released. Okay, so B is going to start moving downwards because it's heavier. Constant downward acceleration of 1.09 meters per second squared. Negligible air resistance and friction. Explain why the acceleration of the mass B is less than the acceleration of freefall. Okay, I won't bother writing this. I'll just say you could word it in a lot of different ways, but the net force on B or the resultant force on B, either one's fine. Resultant force on B is less than the force due to gravity on B because of the tension in the string caused by A. So yeah, I mean, you get acceleration due to free fall. The G, that is our effective gravity on its own. If you start having an opposing force, you're going to get less acceleration. Next up, calculate the time taken for B to fall 1.4 meters. So we can use our S equals UT plus a half AT squared. Admittedly, we can go through, we know where this comes from. We tend to use this formula when we're moving between acceleration and displacement. If you remember all the stuff we've done with accumulations of acceleration into velocity and accumulations of velocity into displacement, they're a little bit more awkward when you're missing out the velocity bit, and we can end up deriving this formula if we go down that approach. But seeing as we're in an exam, we might as well, let's just use the formula. We know what it is, saves us a bit of time. So we got 1.4 equals 0 because we haven't got a u is 0. And then a half multiplied by 1.09 and then t squared. So t is going to be the square root of 2.8 divided by 1.09. Okay, 2.8 divided by 1.09 is equal to, 2.568. So it's going to come out around about 1.6 then when we square root it. 1.60 and then bits. So 1.60 seconds. Let's keep everything staying on 3 significant figures as they've done it again there. Right, calculate the velocity of mass B after falling 1.4 meters. All right, well, the accumulation of the velocity is going to be the acceleration multiplied by the time. So it's going to be 1.60 multiplied by 1.09 because that's how long we've been accelerating for. That's going to give us, so multiplied by 1.09 gives us 1.75 meters per second. Again, illustrating how it's so much easier to go acceleration to velocity than it is acceleration up to displacement. Mass B hits the floor with a speed of that. It rebounds with a speed of that. The time of contact with the floor is that. Calculate the magnitude of the average acceleration. Okay, right, so we've got our change in velocity is 2.47 plus 1.50, because it's gone from positive to negative if we're taking positive as downwards. So it's changed by that amount, and it's done that in a certain amount of time, 3 times 10 to the minus 2. So we've got that is going to be 3.97 multiplied by 10 to the 2. So 397 over 3 is what we've got here. 397 divided by 3, 132 meters per second squared. So, yeah, all good on that one. Let's crack on. Explain why force is a vector quantity. Well, a usual thing is got both magnitude and direction. So that's the 1 mark you get for putting that in. Figure 2.1 shows the force is acting on the water drop on the windscreen of a stationary car. Okay. Got an angle of 30 degrees to the horizontal. They've got that in the picture. The weight of the water drop is that. They've given us that as well. Yeah, so there's nothing in the text that isn't in the picture. Use figure 2.1 to determine the component of the weight of the water drop perpendicular to the windscreen and parallel to the windscreen. Okay, right, so perpendicular to the windscreen, we're going to have 8 times 10 to the minus 5 multiplied by cos 30, so multiplied by root 3 over 2. So 4 root 3 times 10 to the minus 5. 4 times the square root of 3 is 6.93. They've given 2 sig figs here, so let's go for 6.9 times 10 to the minus 5 newtons. So that's our perpendicular, and then we can do parallel is going to be sine of this, so that's easier. You just got to halve it. So 4 times 10 to the minus 5 newtons is parallel, because sine 30 degrees is a half. Determine the magnitude of F. Explain your answer. The water drop is stationary, so we can say that there is F must equal 4 times 10 to the minus 5 newtons. Only want the magnitude of it, so you don't have to worry about the sign on that, deciding which way is up. So yeah, because drop is stationary, I won't write all this out here. Because drop is stationary, so there is no net force parallel to the windscreen. Well, there's no net force in either plane because it's stationary. There's a lot of info in this question, which is the last one in this set. We've got a metal ball held stationary above a tube of oil. Okay, we're going to drop the ball in there, and this must be describing what's happening before and after. So the ball is 0.7 meters above the surface. We got that. Calculate the time taken for the ball to reach the surface of the oil when it's dropped from that height, assuming air resistance is negligible. Right, so we're doing is starting from rest. So we're going to have our S equals a half AT squared. That's the thing that we're going to be using on this. So 0.7 equals G over 2T squared. So T is going to be the square root of 1.4 over G. That comes out 1.4 divided by 9.81 equals that. Square root of that gives us 0.38 seconds, or 0.378. What have they given us here in? Yeah, we have got 3 sig figs. So we'll go for 0.378 seconds. Right, so this graph here is we got velocity against time for the ball as it travels through the oil. So it's hit the oil at time t equals 0. So this is just describing the oil bit. Complete the sentence below. The gradient of the graph is equal to the gradient of a velocity time graph is acceleration. Area under the graph is equal to the displacement. So there you go. That's a displacement from the top of the oil. Maybe put that in just to the top of oil. Put that in just to be clear. Right, use figure point 2 to determine the magnitude of the deceleration of the ball. Okay, right, at point A. This is a nightmare to try and do on this screen because I'm not very good at drawing straight lines freehand on here. But what we're going to want to do is, because we know it's the gradient already, so we're going to want to draw a big tangent line in and then try and estimate from this what we're actually going to get. So let's try taking this over 0.15 then. So who knows what this is going to come out as. So we divide by a time of 0.15. We want something fair as big as possible really on this. So how much are we saying this has changed by? We're going on that line. What's that about? Is that about a half? Up to 2.6 maybe. So I say 2.1 divided by that. Maybe 2.1 divided by, what did I say, 0.15? 14. Okay, 14 meters per second squared. That is an estimate of the magnitude of the deceleration. Right, in terms of the forces acting on the ball, describe and explain this motion at time. So we had time t equals 0.05 seconds and at 0.25 seconds. Right, so at A and B, in terms of the forces, right? So the forces that we've got on the ball when it's in the oil, we got weight going down and we got drag going up. So we're starting off, we've got this negative gradient on here. We've got a deceleration, at least up until B when it goes flat. So in that point, we must have the acceleration is going upwards. So the drag must be greater than the weight. So we can put that in for a start. Drag is greater than weight. So in terms of the forces acting on the ball, so we said that. So if drag is greater than weight, then we can say it's slowing down. Then when we get to B, by the time we've got here, it's now level. So we've got no acceleration. So we can say the acceleration is 0. So the drag must be equal to the weight, which means we're at terminal velocity, because we've got our velocity has come to a minimum there. So that's our terminal velocity. Describe the energy transfers taking place after point B. Right, well, we've still got our GPE dropping. So we know that GPE is going somewhere because the ball's moving downwards. So GPE must be going into something, but it's not going into the kinetic energy. Well, at least not the kinetic energy of the ball. So we have to have it going somewhere else. You don't tend to get a lot of loud noise coming out of a metal ball going through some oil. So it's going to have to be going into thermal. That's about all we got left, really. When you think of losses outside of the system, we're looking at sound and heat normally. There is no sound. It's going to have to be the thermal bit. So yeah, that's all we've really got left to say about that one. Yeah, that's quite a nice question, that, because although you can go through it quite quickly and it seems fairly obvious when you say all of these different things, there's a lot of stuff that you can get caught out on. I mean, people do get caught out on this bit with the forces, because you've still got the object moving downwards. A lot of people maybe don't give enough thought to it and have, okay, this object is moving downwards, so that must be the way that the acceleration is going. But of course, it's slowing down. The acceleration is in the other direction. So our drag must be at least as big as the weight. And if it's slowing down, it must be greater than the weight. So just make sure you don't get caught in that trap when you have these sort of questions.